Okay, let's start. Good afternoon, everyone. Professor Angela kindly asked me to chair the session today. And for me, it's a great pleasure to introduce Pedro Bernardinelli, who happens to be a great friend of mine. And Pedro obtained his bachelor degree in physics at the Institute of Physics across the street. But he also worked here at the IAG with Professor Claudia for a short period of time. And worked most of his time as undergrad with Professor Howard Bramo. He then moved to the US and obtained his PhD at the University of Pennsylvania, and currently is a postdoc at the DiRAC Institute at the University of Washington. He's co-convener of the Dark Energy Survey's Transient and Moving Objects Group. He's chair of the Ehlers Solar System Working Group in the LSST Solar System Science Collaboration, and part of the Rubin Observatory Solar System Commissioning team. Thank you so much for accepting this invitation. The floor is all yours.
Thank you. It's a pleasure to be here. I happen to be in town to renew my US visa, so talked to Lily and she kindly offered me this colloquium slot. I apologize for my voice. I am recovering from a cold because I'm 8 years outside São Paulo. I'm not used to the air here anymore. But all right, let me start my talk. Except that we're having some technical problems. All right, so we are now at the verge of a transformation in the field of outer solar system science, and hopefully I'll have you convinced by that by the end of this talk. So just to set the stage, let me explain to you a little bit what is our modern view of the solar system. We have, in addition to the 8 planets, we have 3 major reservoirs of small bodies. We have the asteroid belt. Oops, sorry. There we go. We have the asteroid belt between the orbits of Mars and Jupiter. We have the Kuiper belt that starts just after the orbit of Neptune. And then we have the Oort clouds, that's the primary source of comets in the solar system, that extends to tens of thousands of AU. So I will be focusing primarily on the Kuiper belt, but also talk a little bit about the Oort clouds and about the asteroid belt towards the end. So the trans-Neptunian region, that's where the Kuiper belt is a region that was postulated originally in the 1930s and 50s by Edgeworth and Kuiper. And the idea is that this was a circular, flattened reservoir of small bodies in our solar system. Basically, these are remnants from planet formation. Every body that didn't form a planet was expected to be in this region as a form of planetism. And in fact, Pluto is one of these bodies. Pluto was discovered in 1930, and it is actually the first trans-Neptunian object. But it was only in 1992 that the second object, Albion, was discovered. And since then, we know of about 4,000 objects in this region. So on the left here is the New Horizons image of Pluto. This was a flyby mission in 2015. And later, this visited Arrokoth, which is this other body on the right, in 2018. And these are examples of both the largest and the smallest objects that we have in the TNO region. So Pluto has a diameter of about 2,000 kilometers. That's 20% of the Earth's diameter. While Arrokoth has a diameter of 30 kilometers. So basically, that's how much I had to commute to come here today. So it's a very small body comparatively. And as objects started being discovered in this region, we as a field quickly realized that things are actually much more complicated than it seemed. There's a lot of surprising dynamical structure in the trans-Neptunian region. So we have here the semi-major axis, eccentricity, and inclination of a set of 300 objects from a survey that I conducted a few years back. And you can see that there's a lot going on here. That's the key takeaway from this picture, from this figure. We have a bunch of dynamical classes. We have completely different dynamical behaviors for these objects. We have the Kuiper belt is not completely flat, but rather objects go to all sorts of inclinations. So basically, there's a lot more going on than just what Kuiper thought was happening. And in particular, there's this region here that I'm trying to point. Oh, I'm pressing the wrong button. That's why it's not working. There's this region here between 42 and 47 AU with low inclinations. That's what we call the cold classical Kuiper belt. That is exactly what Kuiper expected there to be. But clearly, there's a lot more going on. So the modern view that we have today is that the giant planets, they formed in orbits different from the current orbits and then migrated. In particular, Uranus and Neptune They migrated outwards and transported planetesimals into the Kuiper belt. And Jupiter migrated a little bit inwards, also transporting planetesimals a little bit, and formed what we have today as the Kuiper belt. So we have the formation that formed in situ, those are the cold classicals, and then we have the dynamically excited population that was transported by the giant planets. So the idea here is that the TNO region, it's a region shaped by the major dynamical events in the history of our solar system. We have this large-scale migration on the orbits of the planets. We have the fine details, such as how fast and how smooth Neptune migrates, completely changes the structure that we see in the Kuiper belt nowadays. We have objects that have recent or current gravitational interactions with Neptune. So we have objects in resonances. We have objects that are gravitationally scattering off Neptune. There's also the possible presence of a ninth planet in the solar system, but also there are effects such as where the sun formed in the Milky Way that completely shape our Kuiper belt. So just to give you kind of a minimalist view of what TNOs look like, I like to show this image of Arakov compared to a potato. That's a very good approximation to first order of what these things look like. Basically, we have the surfaces of these objects. They're rough. The objects are not spherical, so you can see that in the light curve of the objects. But also, we have the colors of these objects are essentially indicative of the material that from the protoplanetary disk from our solar system. TNOs, their colors are essentially primordial. So what we see today is essentially where the object was formed 4.5 billion years ago. We also have the TNOs can be binaries. There are about 50 systems with well-known orbits. These were measured typically with years of HST time. The separation is about 0.2 arcseconds, so you really need HST or hours of adaptive optics. But there are about 9 binaries that have these wide orbits. They're basically things that we can resolve without the use of adaptive optics, so with something like DECam. And I'll talk about some of these systems later on. So how do we observe these objects? So the primary thing that you should keep in mind when thinking about sources and observations is that these objects move on the sky. So they're not static. TNOs move at about 5 arcseconds per hour. Asteroids move a lot faster. Things like a potential ninth planet in the solar system are a lot slower. And this is a fundamental limit on the exposure time that we have for these objects. Sorry, let me just drink some water. Because if you take a longer exposure, your object will trail and you will signal to noise. So it's very hard to find faint TNOs. The motion of a TNO is very easy to distinguish if you have a dedicated survey strategy. So here, I'm showing you the images of the discovery of Albion, so this first non-Pluto TNO. And these first images were taken at 9 p.m. The last ones were taken at midnight. And if you follow the circles, you can see that the object has moved. So if you take a few images per night, it's very easy. You can see the TNO moving. You can come back a few weeks later, see this again, and that gives you some rough information on how you can trace an orbit and find this object across years of survey data. But not every survey is designed this way, and that's half of my talk. Also, just to finish this slide here, one key idea is that these objects we see reflected sunlight, and because these things are very distant, the fluxes fall as distance to the fourth instead of distance squared. Because basically the light from the sun has to get to the object and back. So going much further is much more complicated because, of course, you have this fourth power. We typically talk about the absolute magnitude h as a proxy for the size. So an object with absolute magnitude of 8 has about 150 kilometers in diameter with typical Kuiper belt albedos. So I'll be talking primarily about 2 surveys here. I'll be talking about the Dark Energy Survey. Oops, my bad. The Dark Energy Survey and the DECam Ecliptic Exploration Project, which are 2 surveys that we've been successful in finding these objects. So the Dark Energy Survey, if you do cosmology, you may have heard of it. It's a major survey for things like weak lensing recently, and it is definitely not made for finding sources. So we mapped 5,000 square degrees of the surface sky during 6 years of data in 5 optical filters. And we've been able to produce a catalog of 814 TNOs. This is one of the largest catalogs to date. And also the DEEP project, the DECam Ecliptic Exploration Project, this is a dedicated TNO survey. Both are using the same camera and same telescope, just with completely different strategies. For deep, we've measured 4 30 square degree fields, so it's a very small area compared to DES. But the way we're doing those measurements is that we have essentially continuous imaging over a span of 4 hours. That allows us to go much deeper than most other projects. And we just finished our first data release where we were able, in one of these 4 fields, to find 110 TNOs. So I'll explain to you basically how we got to this very different results in area and object count. So first, let me talk about the discovery process in DES. Now, once again, DES was not made for transient science of any kind, so we had to work a lot harder than your typical survey. The DES survey strategy is such that we have roughly 1 image every 2 weeks from each point of the sky. So when we come back, the object is now gone, and we have to work a lot harder to find this. So we first had to do this process of transient identification. So the way this works is we have that our moving objects, they appear in only 1 out of the many images we have of the region of the sky. And so we can essentially compare these, and we can see that when we do a co-added image, the object essentially disappears. This is because you're summing your object flux with background noise, and basically this makes the flux smaller, and the object gets fainter and completely disappears from the co-add. So I like to say that this is essentially a digital version of the same process that Kai Tombaugh used in 1930 to discover Pluto. If you don't know the story, what Tombaugh did is he had these images of the sky. These are actually the Pluto discovery images that he put in this apparatus called the blink comparator, and this would essentially blink the 2 images so you could see something moving. Of course, with a survey like DES, you have too many images to do this, and I don't think I would be able to graduate from a PhD if I had to do this by hand, but thankfully we have computers for that nowadays. So we started with our catalog of 10 to the 10 sources that were seeing any DES image, and we were left with 10 to the 8 transients. So these are essentially candidate moving objects. And to kind of as a sanity check to make sure that we know what we're doing, here's a map of every DES image. Each dot here is 1 image in the R band, and the color is the density of transients brighter than magnitude 23. So it's essentially bright transients in our case. And this is in ecliptic coordinates. So at 0 degrees latitude is the ecliptic plane, and in the ecliptic plane we have the asteroid belt. And you can see very clearly that our density is much higher in the asteroid belt than outside the ecliptic. So we're essentially doing the best we possibly can. We're finding asteroids that are indistinguishable from TNOs at this stage. So good job. We can actually find things moving on our data. Then the question becomes, from this 10 to the 8 things that are moving in the sky, how can we find the 10 or so detections from each individual TNO? One way you can think of doing this is that because we're trying to trace an orbit, we need at least 3 detections. There are 6 coordinates, 3 positions, 3 velocities. So with 3 detections, you can, in principle, feature orbits and try to figure out where your object is going. But if you do the combinatorics in your head, 10 to the 8 to the cube is a very big number, and we don't have enough CPU power to do that. So we had to be a lot smarter in our process. So we came up with this triplet-less linking strategy. So the idea is that instead of trying to use the triplet, so a bunch of detections from the same night, we're using 1 individual detection per night to figure out the motion of the object by essentially guessing the distance of the object. We know since, well, Newton, how things move on the sky, because this is basically just pure a pure Keplerian problem. So you can use this information to essentially figure out your typical motion of an object. We did this by targeting every single distance farther than 29 AU. This was a computational bottleneck, not a physical one. That essentially got us all of the Kuiper belt, which was kind of our main idea here. This was a very computation expensive process. We used between 15 and 20 million CPU hours, which is a lot. But we were very successful when we were able to produce a great catalog. So, of course, after we have our candidate orbits, we also have to figure out if they make sense. Because we have so many images of the sky, we've developed this thing called the subthreshold significance test. So here I have a bunch of postage stamps from our real TNO that we discovered. The images with red crosshairs are where we've seen the object, so those are essentially the discovery images. The images in blue are the ones where we don't see the object. And this can be for a variety of reasons. Weather was worse than night, the object rotated and it was much fainter, or this is not a real linkage when we have an actual, basically a bunch of random detections that we think belong to an orbit. So the idea here is, if this is a real TNO, in these independent images, we can stack them and we can still obtain the signal to noise corresponding to basically an object lying right at the detection threshold. So this is here, both the red and this is what happens if you stack both the detected and undetected images. And if you look just into the non-detected images that are completely independent, we also have a significant detection. So this is essentially the best possible verification that we have in a survey like this. So after doing all of this process, we were left with a catalog of 814 objects. This is the second largest catalog to date. The largest has 818, so we were 4 objects shy of beating the record, which it's a bit frustrating, but that's part of life. And we have, of this 814 objects, 813 are TNOs, and one was a surprise, and I'll talk more about it. So just to show you some interesting effects that we can see immediately without thinking too hard about our data, we have essentially no detections at high ecliptic latitudes. This is showing that while the Kuiper belt is not completely flat, it is also not extended across the entire ecliptic plane. Sorry, the entire sky. So it's still focused on the ecliptic plane. And also we have a lack of detections past 55 AU. We have only a few objects, even though we were still sensitive to things at those distances. And this essentially tells us that there was some truncation on the protoplanetary disk. This was already known. We are just showing that with our data as well, and it becomes very clear once you show it like this. But how can we go deeper? First, why do we need to go deeper, right? There are 2 different effects that happen basically when you're trying to discover TNOs. This TNO size distribution, it does something interesting at about absolute magnitude of 8, which happens to be right at about 24th magnitude, 25th magnitude. And whatever this effect is, it's a break in size distribution. It's one of the most constraining things that we can do for planetary formation. So measuring this break is fundamental for TNO science. But also, as I said, we have this 4th power in distance flux scaling. So we need to find these things much farther to be able to probe other structure in the Kuiper belt. So there's this technique called shift and stack, which is basically trying to account for the fact that every time you take an image of a TNO, it moves on the sky. So as I said earlier, if you want to find a static source, there are basically 2 things you can do. You take a bunch of images and you stack them. Your star or your galaxy doesn't move, so that works rather easily. Or you take a long exposure because your galaxy will not trail, so it's an easy thing to do. For solar system objects, both of these strategies don't work. So that's what this shift and stack technique does. So what we do is we essentially stack the images in all possible combinations coming from a real solar system orbit. So this is kind of what this image is illustrating here. We're essentially doing a cone search in image space to find our objects. And that's what we're doing with this deep survey. So our fields, they are rather small compared to other projects, but we are essentially trying to keep track of the nominal drift from Kuiper belt objects on the sky. So essentially, we are following the pattern that objects do on the move in the sky on 1 inclination orbits. So we're essentially trying to maximize our discoveries. And our tests with synthetic objects are showing that we can do consistent discoveries at magnitude 26. So we're going essentially 2 magnitudes deeper than a wide-scale survey like DES. So we have this 90 to 100 images of the same field in our 4 hours. Whoops, sorry. We stack these things. You can kind of see the object in a few of these images if you squint your eyes, but it's very low signal to noise. But once you do the stack with the proper orbit, it's very clear that there's something going on here. and extending these over several years of data, then that leads us to a confirmation that we have a discovery, essentially. So just to put things in context, with DES, we covered 1/8 of the sky, and we found 800 or so objects. Our completeness is at about magnitude 23.8, so we're finding objects with 150 kilometers of diameter. With DEEP, we have 110 objects. We're targeting specifically cold classical, so we're going to low inclinations right at the ecliptic plane. And in essentially 30 square degrees, we found 110 objects of about 50 kilometers in diameter for the typical size. And we only process 1/6 of the data. So we think that once we finish processing the whole data set, and this is being done by our team at UW, we think we'll find between 1 and 5,000 TNOs. Those numbers depend a lot on size distributions and other assumptions, but we're confident that we're going to cross the 1,000 barrier, hopefully. So let me go back to this figure. Talk in more detail about what's going on here. So this is now the sample of 800 objects from DES. A few major features that we can see on this plot. We have these lines here. These are lines of constant perihelion. So basically, that's how close the object gets to the sun. And 30 AU is Neptune, so basically everything is after Neptune. And the vertical lines, they are mean motion resonances with Neptune. I'll explain those a little bit later. So first, let me talk about the classical population a little bit. So once again, here are the cold classicals. That's the hyperpostulated population. But also we have the hot classicals that extend as far as 50 or so degrees of inclination. Those are the ones that were transported by Neptune during planetary formation. There are 3 components in the classical population. Sorry, yes, 3 components in the classical population. 2 in the cold classical population. That's why I confused myself. There's the kernel, which is in a very narrow A range, same major axis range, with low eccentricity and inclination. That is completely an in situ population. And there's this third population that had some low amplitude scattering with Neptune over the 5 billion years of our solar system. And here you can see a typical orbit for a cold classical. The center orbit is Neptune. The purple circle is a TNO, and this is actually an n-body integration, not just a drawing. But we've been able to show that the simple picture is incomplete. First, with the data from DES, we know that there is no possible inclination distribution with just 2 components that reproduces our data. I'll show you later that, in fact, we think there are 3 inclination components that are needed to explain this data set. So that's the first, basically the first time someone has been able to show that there is a more complicated inclination distribution in the Kuiper belt. Second, with the data from DEEP that goes to very small sizes, we do not see the kernel at all. So there's something else going on, and essentially our picture of the classical population, that's the first one that people postulated in the TNO region, is still incomplete. We also have the resonant population. These are objects that are essentially called traps in a mean motion resonance. So their orbits are such that there is an integer ratio between the period of Neptune's orbits and each individual object. So here in particular, the 3-2 population, that's called the Plutino population because Pluto is in the 3-2 resonance. And that's that orbit over there is Pluto, and this is in a coordinate system that is essentially tracking Neptune's orbit. One interesting thing that's going on here is that we are now starting to find objects of very large semi-major axis, basically a very high order resonances. So we're extending to the 10-to-1 resonance. Sorry, my throat is terrible today. We're extending to the 10-to-1 resonance, and our census of the resonances is very incomplete, and we still don't really know how this thing's formed. This could be primordial objects. This is not ruled out by data. This could also be transported by Neptune. We're not really sure. We have the scattering population. So the scattering population is essentially a dynamically active population. These are objects that are much closer, they have much closer perihelia, so essentially they can even intercept Neptune's orbit. So they experience gravitational scattering and they evolve dynamically. And this population is related to the centaurs. Those are the objects. Let me see if I have a slide of centaurs. I don't have a slide of centaurs. To the centaurs, there are essentially a transition population between the Kuiper belt and the Jupiter family comets. We also have the detached population. That is the most distant population in the trans-Neptunian region. They are at very high perihelia, so extending as far as 55 AU in this case. These are objects that experienced scattering in the past, but they're now dynamically detached. And the formation of this population is still a puzzle. There are many facts that we don't understand, and no model can completely explain everything that's going on here. We also have an interesting feature where a bunch of objects pile up near mean motion resonances with Neptune. And the idea here is that if Neptune migrated in a grainy way, so essentially it interacted with a bunch of Pluto-sized planetesimals, and this migration was very slow, this is the only way we can reproduce these objects. And the DS sample was the first time that we've been able to actually have a high significance detection of this effect. And another piece of the puzzle that together with some of my colleagues we've been able to figure out is that if you have the sun form in a stellar cluster and have an encounter very early on with an M-dwarf star, this will essentially make the detached population be more extended. So the interactions between the star and the sun, and basically the three-body interactions with star, sun, and Neptune will drive these populations towards more extended orbits, and this is what we see in the data. This is one potential solution for this, for the detached population, but our picture is still not complete. And we like to call this population the Fernandez cloud. It's essentially a population that formed in this scenario, and it extends into our observable region. We also have these objects called the extreme TNOs. These are objects with very high semi-major axis and very high perihelia. This is essentially a subset of the detached population. And these extreme TNOs are basically the basis of the Planet 9 hypothesis. So this is a hypothesis that started in 2016 that posits that there is a ninth planet, still undiscovered planet in our solar system. And the idea that is that this population is clustered in orbital space. So you can see here that these are the 6 objects that were known in 2016. They're basically pointing in 2 directions. This is not something that you can do easily just with the 8 planets. So you need a 9th planet essentially driving the angles of these objects, putting them in this clustering. If there was no 9th planet, we would expect these objects to be everywhere in the sky. So the fact that we're seeing them here demands some additional explanation. So what can the DES data bring into the table? We actually were the most prolific survey for discovering extreme TNOs. The reason for that is that these objects are dynamically excited, so they have high inclinations. And we basically happen to be covering the high ecliptic latitude, so we were very lucky to find these objects. So we published actually 3 different analyses. I published 2 of them, a colleague of mine published another one, and we used completely different methods, but we all arrived at a consistent answer. The DES data does not require the presence of a Planet 9. So what we're seeing is that our objects are essentially being discovered where we're pointing our telescopes. So I really like this figure from my colleagues that here, how bright each location is means that a survey has pointed at that region of the sky. And you can see that the red dots, the discovered objects, are basically all in high probability regions. So in other words, we are seeing essentially the clustering reflects our observational biases. Of course, we may still be wrong. Even though we were very prolific, this is only a sample of 16 objects, so it's still very hard to basically drive the nail home that this hypothesis is incorrect. But this is our take on this idea of an planet in the sources. So let me go back to this figure. And I was saying that there was one object that was much more interesting than the other ones. And I am not showing it here in the figure because basically, if I made this plot correctly, you would only see that dotted in a clump on the low end. So we found this object with a semi-major axis of 20,000 AU, eccentricity consistent with almost 1. It's 10 to the minus 5 off of 1, and inclination of 95 degrees, so in a retrograde orbit. And this object, this orbit is very clearly representative of an Oort comet, except that we discovered this comet 29 AU away from the sun, so right at our detection limits. Typically, comets are discovered closer than 15 AU, so we were a bit surprised that we were finding something that far away from the sun. This object has an absolute magnitude of 8, which is consistent with a diameter of about 155 kilometers. Some thermal measurements from ALMA later on put this at 137 plus or minus 17, so basically within our error bars. And also, we have here our images farther than 26 AU and closer than 26 AU. You can see very clearly that here we have basically just a point source, and here we have a tail that started to develop in a coma. So in other words, we essentially saw a comet turning on. This is something that's very hard to do because typically we find these objects when they're already bright and active. So this is kind of a unique discovery. And this has a very low surface brightness of around 30 magnitudes per arc second squared. I really like this exotic units that's basically 0.004 electrons per second per pixel in our images. So it's a very low, very weak signal that we were able to retrieve from this object. But why is this object a big deal? Why am I talking about it here? First, we have the comets are usually discovered closer than 15 AU away from the sun. This was the first comet discovery further than 20 AU. Second, only 2 comets before this one had been active farther than 20 AU away from the sun. Even though we typically discover these objects when they're closer, sometimes there's archival imaging, or sometimes surveys simply don't realize that these objects in their data. So we do have images of comets farther than that. So this is essentially the third active comet further than 20 AU. But finally, comets usually have diameters smaller than 10 kilometers. And in fact, the last time someone has discovered on a 100 kilometer scale comet was this one in 1729. So in other words, essentially beat a 300-year-old record for the largest comet ever discovered. And I really like this image here because it's basically the only thing that exists for this comet from 300 years ago. And then the next one was Hale-Bopp in 1995. I think most of you have heard of Hale-Bopp. It was a big thing. And then we are currently the largest comet ever. So that's fun. That was a fun discovery and completely unexpected from our data, especially considering that this was a dark energy project. So let me go back to TNOs a little bit and move on towards the stuff that I'm working now. Let me talk a little bit about photometry. The problem of doing photometry with TNOs is that because they move in the sky, they sometimes fall on top of a background source, like a galaxy, which is what's happening here. So our supernova colleagues, they actually have been dealing with this problem for ages because every time you discover supernova, it is on top of a galaxy. So you have to be able to handle this in some way. So we developed this technique called scene modeling photometry that's basically taken right out of the box from the supernova community, where you're able to obtain optimal flux measurements in the presence of background sources. So the way that this works is that we have a grid of background sources, and because we have many images of the sky, we can forward model essentially this background using the images as basically as a constraint of what is in the background, and this allows us to get force photometry of subthreshold TNOs and the best possible flux measurements. So this is essentially a step above things like difference imaging because this allows you to get the statistically optimal measurement. But the cool thing is that this technique can also be extended to discover binaries. So I was talking about how there are only a few TNO binaries that we can resolve from something like DECam. Well, here are 2 of them. We've extended the population by 25% with this analysis. So what we can do here is that instead of saying that we have one point source, we can try to fit two at the same time and see if there is a statistical gain in your essentially model for the TNO photometry. So we've applied this to the 30,000 detections that we have of DS TNOs, and disappointingly, we were able to find two, which is a very small percentage of our population. But still, these are wide binaries, so they are very rare objects. And we're working on follow-ups with Gemini to try to extend their orbits and constrain, measure their masses, and other things that you can do with a binary link. So every TNO from DES has between 30 and 50 measurements in our 60 years of data. And with this, we can do this probabilistic determination of fluxes and light curves. So basically, TNOs rotate, so their fluxes change. So if we just take the ratio of fluxes to find a color or the difference in magnitudes, we're going to get a wrong answer because we're seeing the TNO at different phases. So by doing this, we're able to phase in this information, and also we get for free a measurement of the variability of the TNO. And this has actually turned out to be a very interesting metric. It's kind of a not studied region of TNO science because there's not a lot of data sets for this out here. So here I'm showing you the mean light curve amplitude and some measurement of the distribution sharpness. So I'm essentially fitting a distribution to the light curves of these TNOs. And we actually found a bunch of interesting things. So the first thing that we found is that big TNOs, they are less variable than small TNOs. This is expected. We expect big objects to be rounder. So that's essentially what we're seeing. But also, we saw some interesting structure in the dynamical families of the TNOs. So we have the cold classicals, they are very variable. They are the most variable population. The scattering is not well measured, so basically the fact that they're here doesn't mean a lot. And this is consistent with a high fraction of contact binaries. So in other words, it's things like Arrow-Koff, where you have two lobes touching each other and the object rotates. We then have the hot classicals and the detached, they are distinct from each other. These are objects that have similar formation mechanisms. So the fact that they're distinct means that there's something else going on that we don't know in the formation of this population. And the same thing applies for the scattered. I was telling you earlier, basically, that the scattered and the detached, they are two sides of the same population. So the fact that their light curves are different is a puzzle. And this is actually the first clear detection of population-wide differences in the TNO variability distribution. And I'll come back to this later on. So the other thing that we have that basically no other TNO survey has been able to do at scale is the study of TNO colors. Most TNO surveys, they usually use one band for discovery, and it's usually very expensive to get follow-ups for the colors of these objects because these objects are typically around magnitude 23 and 24, so you need a lot of telescope time to be able to do these things. But with DES, every single one of our objects has at least a rough measurement of their color. So we can study the structure of the perimeter space. Lily, can you put me some more waters? Because my water bottle is open. So with a data set like this, we need to try hard to essentially study the structure of this parameter space. So we came up with this new technique for TNO colors and actually for statistics in general by extending the formalism for Gaussian mixture models. So Gaussian mixtures are very well known. We're not the first ones to do this. People have been doing this for ages now. But the problem with Gaussian mixtures is that you basically need to say how many components you have a priori. So we came up with this new idea, where we have a Gaussian mixture formalism that accounts for data uncertainties, accounts for selection effects in color space, but also does not require the number of components to be set a priori. So what we get from here is that the resulting model will automatically tell you how many components there are. And this is important because this is telling you how stratified the protoplanetary disk was during the formation of our solar system. So this is the resulting model from our studies. We call this the NERF model, where we have near IR bright population. That's this one. The idea is that this follows this thing called the Redding curve. This is essentially what happens if you get a solar spectrum and make it a little bit redder in each of the bands. And we have this near-infrared faint population that is below this reddening curve. So it's essentially redder than this linear solar spectrum that you're basically varying by changing your reflectivity. And so the implication here is that there's a very clear transition between two types of materials in the protoplanetary disk. And even more remarkable is that a completely different group came up with exactly the same model a few months before us with a completely different data set. We've been having problems in TNO science since people started studying colors, where everyone disagrees with everyone else. This is actually the first time two groups agree. So we're either completely out of our minds or we're actually doing a good job. So this is telling us that basically we're trying to go in some direction here. And here is the same figure that I've shown you many times, but now the color of each object is representative of the color class that the object belongs to. So you can see immediately here that the color classicals are all red. They are completely in the red population. This is once again consistent with their in situ formation. So we know that the population that formed further from the sun has to be redder. But then you look into the dynamically excited population, so the high inclination objects, or the things with high eccentricities, they're predominantly blue. So we think that this also means that the objects closer to the sun, they came from this bluer population and they were migrated outwards, but also the protoplanetary disk extends and transitions in material. So now what we're trying to do is essentially relate physical and dynamical families of TNOs. So basically, how are the color classes distributed along the TNO region? In other words, how can we turn this pretty picture into actual statistics? So what we're doing here is we have that each TNO can be described by essentially a set of 11 numbers. We have the 6 orbital elements, 3 colors, a size, and a shape. That's essentially your lightcurve amplitude. So are there any families that can relate these properties? And how can we study this parameter space? And just as a side note, the population model that we came up with and the associated likelihood for this problem is essentially a 50 plus dimensional parameter space. So we had to come up with very specialized Hamiltonian Monte Carlo techniques to be able to sample this parameter space because traditional Monte Carlo didn't work for our case here. So we've been able to find a few interesting things. The first thing that we found is that essentially one size distribution fits all. So the two TNO color populations, they share their size distribution classes independently of dynamics. So in other words, the size distribution is a function of color, not of dynamics, as people usually think of for these things. But also, the two color classes, they have nearly indistinguishable size distributions. So here you can see that we have basically a 2% error in the size distribution with this very simple model, which is actually phenomenal for our data set. So in other words, we've discovered that there is a universal TNO size distribution. So this means that the same mechanism formed all the small TNOs across the protoplanetary disk from our solar system. And this is independent of where each object formed. We don't really know what this means yet because this is a very new measurement, but this is a very interesting thing that will have huge implications for planetary formation in general. But also, we've been able to figure out that the surface shape distribution is also the same for each color class. So in other words, we have that all the red objects, they share their lightcurve amplitude distribution. And as I said earlier, we have the cold classicals that are the red objects. They're also the most variable. All red objects in the other population are also more variable than all the blue objects in all populations. So in other words, the lightcurve amplitude or the shape of the object is also a tracer of where the object was formed in the protoplanetary disk. And this solves our lightcurve amplitude and dynamical problem. We now know what's going on here. We have different mixtures of each color class, and that's why we're seeing the different lightcurve distributions. And the red population, being more variable, it's consistent with more contact binaries or more elongated objects. So it's basically the shapes of these objects are actually different. We also were able to study relationships between color and inclination. This is something that has been studied to exhaustion in TNO literature, and there were correlations that people were measuring for years now, but there was no actual explanation for what was going on. So here, we've been able to discover that there are actually bimodalities in color and inclination for a few populations. So we have the hot classicals, the Plutinos, and the objects that are in the main belt resonances. So these are resonances inside the Kuiper belt. They're all bimodal in inclination. So in other words, the red objects, they have a more constrained inclination distribution, so they don't go to as high inclinations as the blue objects. And this is, we think that this is, once again, because the red objects, they formed further from the sun, so they were less migrated by Neptune and not as scattered during this process, so that's why they're less dynamically excited. And this is also the first detection of dynamical substructure beyond the usual cold and hot distinction in the Kuiper belt. So this is essentially a completely new picture of inclination distribution for TNOs. And this is the best measurement out there that we got for free because we're trying to study colors. So then you can ask here, are we done? Have we completely solved TNO colors and no one has to study this anymore? And the answer is no. We also were able to discover that the color distributions are asymmetric. So if we split each one of the Gaussians that I showed you between the bluer and the left half, bluer and redder halves, we find that the populations are not isotropically distributed. So we have that the detached population is typically bluer than the other populations in the blue populations. Basically, the bluer objects are bluer and the red objects are redder. So we don't really know what's going on here. And we think that this is basically a detection of a non-homogeneity in the protoplanetary disk. If you take any sampling from this homogeneous population, you would expect some form of homogeneity. Because we're not seeing that, this means that there is some form of non-homogeneity. So in other words, this is a completely new paradigm for TNO populations. We have that color, sizes, and amplitudes, they're all tracing the same physical process, and the dynamics is tracing the dynamical history of the solar system. So now let me talk a little bit about the future, and then we can have a few questions. I think most of you may have heard of the Legacy Survey of Space and Time, or the Rubin Observatory, or LSST, Large Synoptic Survey Telescope, if you've been in this field for a while. So this will be a 10-year project covering the entire surface sky roughly every few days. And the operations for LSST will start basically in a year. The commissioning camera is being installed this week, I think. And the big camera, which has 3.2 gigapixels, is already at the summit. So we'll be starting taking data very soon. So what happens for solar system science when we turn LSST on? This is a simulation made by the team at UW that's called the Rubin Data Preview 0.3. This is a solar system catalog at scale for LSST. This has about 20,000 TNOs. So that's a factor of 5 more than we know of today. And in fact, we think that we're going to see a factor of 10 more TNOs. So every population in the solar system will have a very high increase in number of objects, basically because solar system science is one of the pillars of Rubin. So for TNOs in particular, we think a factor of 10 more objects will be discovered, but also every other population will have a similar increase in discoveries. And to be able to actually quantify this, we have this project called SORCA. SORCA is an open source software that I'm developing with a few colleagues, where we're trying to enable large-scale simulations of LSST. And here is some analysis that we have as part of our data preview. They're showing you basically when LSST will discover each object. So here is basically how many years have passed since LSST started, and basically it's a cumulative distribution for TNOs, near-Earth objects, main belt asteroids, and long-period comets. So NEOs and comets, they have essentially a continuous flux of objects being discovered. As objects come from wherever they are now and move into here, we see them, and that's why we have this flux. But main belt asteroids and TNOs, because their distances don't change that much for the period of 10 years, we think that the overwhelming majority of objects will be discovered within the first year of operation. So for TNOs, basically by 2026, we have found 6% of the total TNOs that LSST will discover. So this will be a boom in TNO science in the next few years. And here is what happens after 10 years of observations. So I was talking about DES, how every object has between 30 to 50 observations. With LSST, we expect 100 to 200 observations per band. So all of these analyses of colors and light curves and etc. will become much more powerful and much more statistically significant with LSST. But LSST will not find everything that is in the data. This is the LSST design. So this is what LSST was meant to find. LSST has some, not set in stone, but very hard limits for discovering things only as far as 150 EU. This is basically of the way that the survey was designed, and the pipeline is meant to find things like asteroids. So that's why we have these limits. But if you have something like a Mars-sized object at 400 AU, it's still bright enough for LSST to pick it up. And mining this data set will be basically how we're going to find if there is an ice planet in our solar system, or if there are other interesting objects there. And beyond that, if we can do shift and stack with LSST, and this is something that we're doing with this project called KBMod at UW, we expect that instead of finding 40,000 objects, we're going to find something like 100,000. This will get us, with 1 year of data, basically a 2 magnitude gain, 2 magnitude zipper, basically, for our objects. So yeah, LSST will be fun for people who do source science. And finally, let me just show you this figure. Each one of these dots here is a potential location for Planet 9. This is how it was simulated by Mike Brown, Constantine Batygin at Caltech. And right now, ZTF, DES, and PAN-STARRS have ruled out 78% of the parameter space. But there's still 20% of the parameter space left. And LSST will cover the majority of this space in the first year of operations. So in other words, in 1 year, there might be a new planet in the solar system. We'll see. I think it won't be. That's kind of like the other half of my talk. But if you're optimistic, in 1 year, there will be a new planet out there. And well, that's all I had. I'll leave my summary and I'm open for questions.
Thanks so much for your talk. Does anyone have
Excellent talk. Thank you for that. I have 2 questions, if I may. The first one is, which parameter did you use to quantify the variability in the light curves? And yeah, and the second one, could you briefly talk about the Hamiltonian Monte Carlo approach?
Yeah, so can you repeat the first question? Sorry.
Yeah, which parameter did you use to quantify the variability in the light curve?
Okay, so the idea that we were doing is that we think that the TNO light curves are essentially completely physical. They come from the object rotating. So we know that the easier way of doing this is you assume that you have a sinusoidal light curve, and you essentially measure, but you have a sinusoidal light curve at a random phase. So you can marginalize over this phase, and this will give you a posterior on the light curve amplitude. I'm happy to show you the math. It's actually fascinating, and it's a very fun trick that we played. So essentially, you don't need to know the period to be able to essentially have some variability metric. So the second question was about the Hamiltonian Monte Carlo stuff. So Hamiltonian Monte Carlo it's this fantastic statistical technique where you have your likelihood, and you posit that this likelihood lives on a thing called basically Hamiltonian space. It's the same thing you would do with Hamiltonian classical mechanics. So you essentially make your parameters your dynamical variables. You posit momenta, and you solve Hamilton's equations of motion, and that's how you get your posteriors. This is much better for sampling complicated parameter spaces like this. The problem that we have, let me go back to that slide. The problem that we have is that this parameter here, they're essentially telling you how much of each component we have in our model. And variables like this, you can very easily show that they have to be 0 or greater, and they can't sum to more than 1. So the way we solved this problem was actually by playing tricks from molecular dynamics, because they solve similar problems where you have that your molecule can be at some distance, etc. So you can use the same technique to sample this parameter space. And I think we're going to make the code open source. I still have to ask my collaborators, but that's what we try to do generally, so I think we'll do that.
Any more questions?
A curiosity. What is the physical mechanism behind the migration of the large planets during the formation of the solar system?
Yeah, that's a great question. Let me go back very far. There we go. So basically, we think that what triggered this instability was the orbits of Jupiter and Saturn crossing mean-motion resonance. So they were having some friction with the planetesimals, and this was already driving the torques of the orbits a little bit. They cross this resonance, and they start migrating outwards. But for things like exoplanet systems, I know there are other mechanisms that I don't know off the top of my head. But this is what we think happened for our solar system.
Can you have any physical information about the physical constitution of these bodies from the colors?
Oh, that's a great question. So the colors of these objects are actually very hard to tie to physical material. Basically because they're very similar to solar colors, so whatever reflects things a little bit, we can get there. But now with JWST, we have spectra of these objects. It's usually very hard to get a spectra from ground-based surveys. There are only a few. There's a big project at JWST called DISCO TNO that measured a spectra of, I think, 70 TNOs. And we know that they have basically a bunch of CO and CO2 in their surfaces. But this is still a lot of uncharted territory. For most TNO color science, we just assume that the color is just a parameter tied to the composition of the object. We don't really know the relationship.
Okay, thank you.
We have questions online?
Yes, I do.
And then there's one online as well.
Can I make? Hi, Pedro. Very interesting talk, thanks. I have a quick question. Any new insights about Kuiper belt out of this survey?
So our primary new insights were this idea of the star cluster formation. No other data set had been able to actually show this as well as we have. And this color stuff is completely new. The largest TNO color survey before us had only 80 colors. We have a factor of 10 more. So there's basically a lot of things we can do here.
Right. Mm-hmm. Thanks.
Hello. I have a curiosity also. It's you said that there are some TNOs that are born in situ, and then there are some that were brought there by Neptune. Can we have also some accretion, some TNOs that came from interstellar space and accreted?
That's a great question. So that's actually one of the other potential explanations for this clustering that we see here. Sedna is one of these candidates. Sedna has weird colors that don't really represent the rest of the solar system. So one of the hypotheses for the formation of Sedna is that it was actually captured in the birth cluster of the solar system. But also we have, in the asteroid belt, we have that basically there are a lot of collisional families from asteroids that collided, and then you can tie their composition and dynamics. For the TNO region, we have only one collisional family. It's the Haumea collisional family. So we think that the population is still very representative of formation.
Any more questions? Final questions to Pedro. Otherwise, let's thank the speaker again.
Thank you.